Thank you for tuning in. This is a short tutorial about 10 minutes where we'll discuss modeling of the film stack for OLED encapsulation. It's a 10 layers film stack with a double layers tantalum oxide and aluminum oxide on a glass. So we'll create a film stack with these 10 layers, include a correction for the backside reflection from the back of the film glass, link the layers and send constraints to limit the number of their calculated parameters, adjust the optical constants, and finally determine the thickness of the layers. First we'll use the standard film stack and we'll change the substrate to void because we have a backside reflectance, so the actual substrate is our void or air. The first layer will be our glass. So this layer we need to make it thick so that it will be incoherent. We don't want to have any interference within the layer. Okay, here is a non-coherent. So we'll have only backside reflectance but no phase. That's the idea. And now we'll go to the film stack editor and add tantalum oxide here in the materials. Yeah, so here it is. Yes, we'll add it and we'll set the thickness of this material. It's 0.1 micron, 100 nanometers. Now we'll add aluminum oxide. We have it in the library. Set also 0.1 micron. Now we'll select both of these materials and replicate it 4 times. So we'll have 5 pairs of these materials, layers, altogether 10 layers. We'll link the layers, tantalum oxide and aluminum oxide, separately into groups, and materials are automatically linked. So now we'll have only 2 parameters. We'll load the measured data. Here is the visible spectrum, and just check what is our generated film reflectance from our generated film stack, how it is connected to the measured data. Not very close. So we'll start with the setting constraints for all their thicknesses, so that when we calculate it wouldn't go wild and go some strange values. So we need to do it only for 2 materials. All the linked materials layers will be automatically done and the parameters propagated. So we try to calculate adjusting the thicknesses, but doesn't look very good. Not much difference. So now we'll try to adjust the optical constant of tantalum oxide. Okay, this is better. Not perfect, but we're on the right track. So so I think we now need to adjust the backside reflectance scale factor, because not all the light reflected from the backside. Okay, yeah, so it's a little bit scaled, a little bit better, but we need additional improvement. So maybe we need to, yeah, let's try another time. Okay, so it's now fit better. Yeah, so we'll uncheck the optical constants here. We get as much as we can, and let's see what we can do else. Yeah, let's see if we can adjust aluminum oxide. It's probably okay. Aluminum oxide is relatively stable. Yeah, no change, no much improvement. So our next step is we need to allow thicknesses to float. We need to basically unlink the layers and Oh wait, we have a little problem here. So we put constraints, but constraints are too tight. So we need to make the range wider so that thicknesses can be adjusted more accurately. Otherwise, they're just bumping into limits, and it's not good. So we'll just change it, make it a little bit wider in 2 layers, and it will propagate to other linked layers. And see. Yeah. So yeah, now we need to look if we can unlink the layers and allow the thicknesses to float and adjust. See if that that will improve a little bit the fit and thicknesses. Okay, so the fit is a little bit better, and thicknesses adjusted. So they are not identical, they're a little bit different from layer to layer, as you would expect. Difference is small. So we'll try to see if we can improve. The fit is already good, but maybe we can improve a little bit. So we link back the materials. We cannot link the layers because they now have different thicknesses, but materials are still the same. So we link the materials and try to see if we can adjust the optical constants more while we allow all the thicknesses to float differently. Yeah, so we'll check the thicknesses first, and try to see if optical constants can be adjusted. Now it's about the same. So we'll uncheck it and try aluminum oxide. Okay, so I think we're done. It's as good as we can get the fit. So now we'll check and see what the results are. So we can review the results, save it on a clipboard, and copy it in our notepad. That's one way of reviewing results. We can see all the thicknesses and all the film stack. Another way is to export measured and calculated data. So our results with all the data to the Excel file, and review it in Excel. So here we can save it to file, and it basically will have measured data, result of the model, and thicknesses that we measured. Everything in one file. So let's give it some name recognizable, and look at the file after we save it. So here's this file, and we see it in an Excel spreadsheet. All the thicknesses. So this is 2 columns of the measured and model data, and at the bottom there is actual measurement results that we reviewed before. This is it. We created a film stack, analyzed the data, get the thicknesses, exported the results, and thank you very much for tuning in. and let us know if you have any questions. Thank you.